not to make you sleep. And my own teacher is there. So if I am telling anything wrong, and I am telling he is responsible because you have not taught me well. I'm sorry, on a lighter note. So anyway, in line with whatever that we are discussing, I thought I'll give a brief overview on the material aspects for effective precast design, right? So we need to understand. So we talked about quality assurance, quality control. Unless we choose the proper raw materials and do it properly, then you will not get the product correctly, right? So we need to understand how the constituents of concrete actually work and how the manufacturing has to be done. Then only the precast will become successful, right? So that's the whole idea. Just a quick outline, just one slide on history of concrete, and then I'll talk about what are the basic constituents of concrete. It may be just a quick overview for most of you, but I'm going to talk in the context of precast technology, right? And then we'll talk about short-term properties, focusing on compression, how the stress-strain behavior for normal concrete, high-strength concrete. We at IIT Hyderabad, particularly my research group, we are doing a lot of work on ultra-high performance concrete. For last 7-8 years, I think 2-3 PhD students are working on it. I'll briefly highlight because I personally believe UHPC has a very strong role to play in the precast systems as well, right? And we'll get into some aspects of long-term properties like creep, shrinkage. Because again, from precast, as Professor Sri and I think Professor Amlan also talked about, precast and pre-stress, they go hand in hand. If you want to effectively utilize the precast technology, most of the time we apply some form of pre-stressing, right? So when you do pre-stressing, these long-term deflections will become very important. And most of the time, the design of pre-stressed elements which are longer in span are governed by the serviceability criteria. 90% I can say. Hardly the ultimate strength will actually govern the design, very few times, maybe for two-way shear, punching shear. But otherwise, it is actually the serviceability, the allowable stress levels, and the cracking and deflection is what actually will control the design, right? So we will talk about some of these aspects that also will play a role. Finally, little bit I'll talk about pre-stressing steel, right? Okay. Then finally, this is, I'll talk about some of the work that we are doing on hollow core slab. I think Professor Amlan as well as Professor Sri talked about in precast, which is a major component that is being used. Can anybody guess? Tendons, of course, we need to use tendons for. Of course, concrete. Which component? You have beams, columns, slabs, right?
This is coming due to this.
Which one? Yeah. Okay. So, among various precast components, my question is, which component is very widely used? Wall panels. So in that also, it's the hollow core slab actually is one of the most widely manufactured element by the precasters. Because the hollow core element can be used as a slab element, it can be used as a wall panel, so it has multiple applications. So that's the reason hollow core slab, if you look at the market share, almost about 57% of the volume of precast components are actually hollow core slab elements. So I'll briefly talk about what are the, just quick outline. I think again, there are a lot of developments that happen at the material level, and precast is the industry that is quick to adopt the developments in the material because you produce components in the factory controlled environment. So there are a lot of variables that you can control, which is not otherwise possible in cast in place construction. So the adoption of new materials and technology is actually quickly taken up by precast industries than the conventional cast in place construction. So that's the reason there. In fact, I would say industry is much ahead. We do some studies at the lab scale. at a small scale, but precast then, pushes the envelope, right? So we'll talk about it. Okay, so just quick outline, do you know who's John Smeaton? How many of you know John Smeaton? He's a British engineer. He's also called as father of civil engineering, right? So he was one of the pioneers in promoting hydraulic lime-based concrete for variety of construction. Because hydraulic lime-based concrete, when it is in contact with water, right, the hydration process happens for a long period of time, and he was very pioneer in paving the way for development of Portland cement, which happened little later. So of course, Roman concrete, we know for more than 2000 years it is there. That is also hydraulic lime, but somehow in between we got lost. Then it was actually John Smeaton, who is one of the very famous civil engineer. He is also called as father of civil engineer, right? So he promoted the use of hydraulic lime for concreting applications, right? That actually paved the way for Joseph Asphodel to actually invent modern Portland cement. Then, the concrete construction started rising in a big way, right? So if you look at it, we are only about modern reinforced concrete. If you look at it, we are not more than 150 years or so. Cement was invented in 1824. Then Joseph Monnier was a French florist. He was making flower pots, and the flower pots were cracking, and he put some steel wires, okay? Because we know that it is going to develop hook tension. To arrest the hook tension, you need to have some reinforcement, right? Then Hennebeck was the one who invented reinforcing systems, shear reinforcement, all those things, how do we put it, as per the documented evidence. Then pre-stress, okay, 1933. So if you look at it, pre-stress concrete also hardly it is about 100 years older technology. But if you look at the evolution of construction, we have a lot of historical monuments which are standing for more than 15, 16 centuries. But those are all, if you look at it, those are all stone masonry, and spans are very limited. So, but modern construction, we want to span for a longer distance. The moment we want to go for longer spans, the only way we can do with concrete is by putting pre-stress into it, right? So again, he's also called as father of pre-stressing. Then entirely, corrosion is a big issue. Then people started exploring alternate materials, and fiber reinforced polymer is one of the effective means of using construction. Even in 1957, in Monsanto, there is a company, they did a single story classroom structure entirely made of FRP. But again, fire resistance is a big issue, right? So fire resistance is always a big issue. And that's why concrete constructions are very popular, because they're inherently have a very stronger fire resistance, right? But anyway, so this was on a trial basis. Then to address durability, high performance concrete came. So what is the meaning of high performance concrete? Can anybody? What is it? So when you say performance can be defined in multiple ways, right? So what is the meaning of performance? Performance can be defined in multiple ways. Workability, strength, flexural strength. Okay, mechanical property you're saying. Anything else? Is the most important thing is the durability, right? So high performance concrete, you don't talk only in terms of strength, but talk more in terms of durability, right? You make the microstructure so dense so that your deleterious substances like chlorides, sulfates or water cannot get into the system and start the electrochemical corrosion in a reinforcing system. So high performance concrete was invented in 1970, and then UHPC in France, they developed it as early almost 30 years ago. But then it was on very small scale applications, lab scale studies. In the last 20 years, there is a lot of development in the chemical admixtures, and our understanding of the material aspects also has improved. So that has actually paved way for increasing use of UHPC in concrete construction. So anyway, why I'm talking about it is precast industry is the first one to adopt any innovations that are happening in the material technology. So right from, because as I told you, you do manufacture the elements in a factory controlled environment. So a lot of things you can control it very tightly, right? So that is the reason. So precast is the wide adoption of, So now we are talking about, UHPC, then we are talking about zero slump for variety of precasting applications, right? Right, so just now material aspects, as you know, broadly the constituents of concrete, you have, of course, cement, which is a binder, which we also call as a glue, that is going to glue all the things together, right? And then you have, in the modern day construction, we try to use a lot of the supplementary cementitious materials like fly ash, slag. Fly ash comes from thermal power plant. If you look at from energy point of view, 70% of the energy that actually comes from thermal only, even now. Right? So you have abundance of fly ash that are available, particularly in Asian countries. Of course, in the US and Europe, the
TBC has the largest.
largest. In fact, they don't know what to do with fly ash most of the time. Right? So, and then you have fly ash, the bottom ash also is there. Right? Fine aggregate, coarse aggregate, all those things. Now, in the last 20-25 years, there's a lot of development that has happened in superplasticities also. So, which is also called as high range water reducer. Now we know the simple basic rule, right? Abraham's rule, you may be knowing. Higher the water cement ratio in the system, lower will be your strength. So if I reduce the water cement ratio in my concrete material aspects point of view, I gain higher strength and higher performance. In fact, let me ask you this question. What is the typical water cement ratio that is good for concrete? Can anybody take a guess? 0.35? 0.4. Why is it 0.4? Why do you think 0.4 is a good number? There should be some rationale, right? Why do you think 0.4 is a good number?
Recommended way. Actually, as per design, I will make it, sir.
Okay. Can I not go lesser? Why I cannot go lesser water cement ratio or water to binder ratio?
So because it needs reaction, sir. In reaction cement, we need at least minimum amount of.
What should be the minimum?
0.3, sir. I think so. For each species, 0.3.
Actually, you don't need more than 0.2. If you look at for the normal compositions of cement that what we use in concrete, you really don't need water to binder ratio more than 0.2. Okay. So, as you said correctly, typically we go for 0.35, 0.4, 0.45 also regular constructions, because this chemical admixture that what we are going to add, superplasticity, is costly. So, if you want to reduce the cost, so easiest thing is to add more water, right? So, for complete hydration of cement, actually you don't need really more than 0.2 water to binder ratio. So, if I am putting 0.4, what is going to happen? Workability will be high, correct. But what are the costs that I am paying for that?
So strength will be lower, durability.
Strength will be lower, durability what will happen?
Yes, sir. It will be lesser.
It will be lesser. So, strength is also going to be lower and my durability is also going to be lower, right? Because whatever that unutilized water in the system, in cementitious system, that is actually the culprit that we are going to talk about, creep and shrinkage. So that will try to come out of the system and that will create more problems. Okay, so if you want to have a more durable concrete, somehow I have to have a low water to binder ratio in the system. Now the advancements in the chemical engineering in terms of your superplasticities or our understanding how the superplasticities work, that helps me to correctly dosage the superplasticities requirement, so that even with low water to binder ratio, I can still achieve hydration without compromising workability requirements. So that's the idea, right? Now, with respect to UHPC, if you see here, we are going to use again a lot of supplementary cementitious material like fly ash, GGBS, microsilica. And where does the microsilica comes from?
From chips, sir. Chips, waste of chips.
What is the waste of
Precast
chips?
chips.
In the, the silicon manufacturing of these chips, there is a lot of silica comes. So there is in fact, it's a costly material. It's a very fine powder, right? So it is fly ash, GGBS, where does it come from?
From gold and GGBS.
GGBS blast furnace slag. So, again in India we have steel requirements are so humongous, right? So, in fact, roughly they say 1 ton of cement, in fact, almost leads to about 0.8 tons of GGBS. slag, I should say. Slag, again, they go through multiple purification process. So we have a humongous, we don't know what to do with blast furnace slag also. So that's the reason, we try to take advantage of these properties by putting them in concrete. That will help you in multiple things. Okay, so in UHPC again, we add a lot of steel fibers. I do not want to get into that. And we want to gain strength. Again, I told you, if you want to have high strength, now I need to have low water to binder ratio. So with low water to binder ratio, still if I want to have flowability and durability, only way I can do it is by adding more water reducer, high range water reducer, right? In addition to that, we also put lot of steel fibers. And these steel fibers are actually micro steel fibers. I think some of them are here. I will just pass it on. We have different types of fibers. Typically what we have is this small, the brass coated fibers, which are straight fibers, which is less than 0.12 millimeter. And roughly it is about 13 millimeter or so. So I'll request, to pass. And you also have hooked end fibers are also there. Normal hooked end fibers are there. Even in the micro fibers, again, we have hooked end fibers are also there. Different types of fibers are there that I'll just pass it on so you can look at it. Okay, you handle it carefully. So now again, why do we need to add fibers?
Sir, it will reduce the shrinkage cracks. It will not allow the concrete to fail recognition.
So can we say it will give me crack resistance?
Crack resistance, and it will help in reducing the size of the slab.
Well, that depends upon multiple, so many factors are there. So, but as you said correctly, the steel fibers are added to give me the crack resistance. Depending upon how much I want, I can tailor the dosage of the steel fibers, right? Anyway, so these are the conventional constituents of concrete and UHPC constituent that we talked about, right? And now let's quickly, talk about, I think these are all, we know that cement is the binder. And of course, you have different types of cement is also there. High early strength cement, right? And sulfate resisting cement, rapid hardening cement. So many products are available. So we need to choose a product according to the precast component that actually we are manufacturing, right? So all of this, again, water. Again, what kind of water we need to use for concreting?
pH 7.
Is it only pH 7? So is it usually typically, what is it? 6.5 to 8 pH. Is that the only parameter that we need to look at? You're right. Water that is suitable for drinking is what recommended for making concrete also. What is the other important thing that we need to be very careful? Chloride should be lesser, because most of the time the RMC people or even regular construction, what we do is we try to use groundwater for making concrete, particularly in the low residential segment, G+1, G+2 kind of construction. They don't go to RMC. They make concrete on their own, right? So what they do, they use the groundwater, tap water, right? In the tap water, if you don't do the testing properly, what will happen? The soluble chlorides are going to be very high. And the moment you put chlorides in the concrete, which is dispersed through the entire medium, that's it. Your corrosion, durability is compromised, right? So this is very, very important factor. Even in RMC plant, if you are the client and if you want to verify how good is the concrete, the first thing that you need to do is check the quality of the water what they're using and to make sure they are within the permissible levels of chloride. Otherwise, if chlorides are there in the system, within 2 years, in fact, we have several buildings in the NCR region close to Delhi, though it's a very dry region, nowhere close to marine conditions, right? Still, the lot of buildings have corrosion issues because they were using the groundwater which is full of chlorides. So that's one thing that we need to be very careful. So in addition to that, I told you, chemical admixtures, there are so many products are available. Similarly, mineral admixtures also we try to use so that you can tailor the concrete mix design according to the mechanical properties that what you're actually looking at, right? So this is what it is, okay? So of course, for precasting or most of the applications, if you have heavy congestion of reinforcement, we need to have a flowable concrete. Now the flow of concrete, how do you tailor? Again with superplasticizer or by proper gradation of your aggregates. If you have large size aggregates in the system, then it will not flow easily, right? So if I want to have a flowable concrete, then I have to really, the powder content should be on the higher side, right? Okay, right. So high strength concrete, again, I told you that as per the definition of IS 426, anything that is more than 65 to 100, we say that as a high strength concrete. And how do you get high strength concrete? The basic thumb rule is to reduce the water to binder or water to cement ratio. And in addition to that, we put super plasticizer to improve the workability. And in addition to that, we also use mineral admixtures. Now, what is the role of mineral admixtures?
So it will be used as fillers in concrete.
Huh?
Fillers.
They are not only going to act as a filler because they are finer particle, it will help in filling. In addition to that, they will also help us in creating this additional calcium silicate hydrate products. Okay, so that is what we are going to look at quickly. Basic reaction of cement, it's hydraulic. So the modern cement is hydraulic in nature, right? The moment you add water, then only the reaction starts and then you get the product. But with the pozzolanic reaction, what happens? There is a chemical reaction that is going to happen between reactive silica or alumina, which are present in the fly ash or your GGBS, and portlandite. What is portlandite? Portlandite is nothing but a calcium hydroxide. So the reaction will happen between them, then your additional calcium silicate hydrates will form. So you will get more denser network structure inside the concrete. More denser the network is, the water or other deleterious substances cannot actually enter the system. So that's the whole idea, right? So basics of reaction, I think this is just for the sake of completeness. So if you want early strength, then your cement should have either C3A higher or C3S higher. This is what it's going to react faster, right? But if you want later strength, CTS should have more. Okay, the cement composition also, depending upon whether it has high C2S or high C3S or high C3A, your reaction is going to be faster. So in precasting, as we told, long line method of production, if I'm making a hollow core slab, I think Professor Ramlan as well as Professor Sridharan told, what is the turnaround time? Maximum, what is the turnaround time? Is it 24 hours, right? So that means about 20 hours, I need to cut the strand so that I can remove it and then get the bed ready for the next casting. So for such kind of applications, then I need high early strength, right? So if I need high early strength, what kind of cement I need to put? The cement which is having higher, right? So it's got higher C3S and C3A, right? So that is it. Okay, so this is again basic cement chemistry. So you know that initially when we put the cement in water, it is in fluid suspension, then it is going to set over a period of time. Now this is what more important. So this again, calcium silicates combined with water produce these products of hydration, which is the denser material that is giving me all the mechanical properties. In addition to that, you also have calcium hydroxide that is produced. Now in between them, if you look at it at micro levels, at different levels, you have capillary pores which are all connected, which are typically more than 10 nanometer of different sizes, let's say. And then gel pores means within the calcium silicate hydrate gels, you will also have some pores which will be less than 10 nanometer, right? So now, which one is you think is going to create more durability issue? Is it the gel pore or is it the capillary pore? So which is all connected? This gel pore is, the gel pores you're looking at in this graded particle. It's very small, right? But the blue color is all connected, right? Which is a capillary pore. So capillary pores actually creates the passage for the water to actually escape out of the system. Now I told you, what is the major durability concern that comes from? It is come from the excess water that is in the system. It is trying to escape out of the system, right? So if I have more capillary pores, more water can easily go out of the system, right? So which we need to be careful. Okay, so quickly. So again, we know that initially the moment you add water, quick heat comes and then initial setting time and then your product forms. And if you look at this green color as the size of your cement grain, then hydration as a hydration process goes on, the size of the cement grain will reduce with more and more CSH product that are forming, right? So you know all these things. And after a certain point of time, after the final set time, the heat release is going to come down and the hydration process will continue for a very long period of time, right? So these are the primary reactions. Now what we are trying to see here is, these are the basic reactions where this calcium silicate hydrate form. When I have more C3S, you can see that you also form calcium hydroxide, which are weak and soluble. That's why if you look at it, if you have some cracks in the system, you will see white marks. Why does that white mark comes? It is actually basically the leaching of the calcium hydroxide. So that is what it is. So somehow what we try to do is, whatever this calcium hydroxide, which is a weak and soluble product that are in the system, I want to convert this into an additional calcium silicate hydrates. How do we do that? That's what I told you. Supplementary cementitious materials, they help you in achieving that. Okay. Oh, so quickly, now let's get into now we understand, nutshell, in a very quick way, what is the basics of cement hydration and how does this happen? Because this is going to have an influence on your short-term as well as long-term properties. So let's look at now what is the short-term property. Now complete stress strain curves, ideally we want to establish the complete stress strain curve for our calculation purposes. You do design for precast pre-stress system. How many stages of design that we check? Anybody? How many stages of checks that we do in a pre-stress precast system? We see in reinforced concrete, we do it at 2 stages, right? What are that? We design for ultimate conditions and then we check for serviceability. These are 2 main limit states that we check. But in pre-stress, what are the extra thing that we need to do? It is also during the transfer of pre-stress, right? So 3 stages we need to check. So now concrete strength is not the same in all the 3 stages, right? In addition to that, you also have losses that I think Professor Amlan talked about. So material property is changing, over a period of time. In addition to that, I have to deal with losses also. So depending upon at what level that I am doing the analysis, I need to consider the proper material property, also the proper losses. I have to account them in my design. So that's the important thing, right? So anyway, to do that, I need to know all these 3 important parameters. In compressive strength, usually we call this as F prime C, which is F prime C actually denotes for cylinder compressive strength. Okay. In India, what is that we use as a standard? Cube or cylinder?
Cubes.
Cubes, right? So why do we use cubes? Why can't we use cylinder? Just it's easy to do, right? So it's easy to do, and we have been carrying the legacy from the Britishers and we have been carrying forward that. But actually, if you look at it, cubes will give you higher strength. It is not the true representation of the material property. If you want the actual true representation of the material, you know the Saint Venant's principle. I need to have a material plane that is free from stress concentrations, right? So I need to move at least a distance d from the, the loading point. So ideally, if you want to have actual material property, you need to test a cylinder or a cuboid with at least an aspect ratio of 2. Then only you'll be free from the boundary condition effect. Okay. Anyway, so then in addition to that, we also need to know what is the tensile strength. Tensile strength is measured in multiple ways. Okay, this could be pure tension, it could be splitting tension, which is an indirect measure of tensile strength. Then you have rupture strength. What is the meaning of rupture? Rupture means in bending strength, bending flexural strength. What is it? That's what we're looking at, right? So that, and typically what we use is a 28-day concrete strength. Okay, but I told you this is for ultimate checks, but not a transfer. Transfer, when I am doing the long line method of production, when I am doing the pre-stress transfer, let's say at 18 hours, then what should be the material property I need to do? 18 hours or 24 hours. It is a material property that is at that time, that is what we have to use, right? When you do hollow core slab or a long line method products, when you transfer the pre-stress, that's going to be at a very early age. So that mechanical property is what we have to actually use. But this is for ultimate capacity, typically we use 28 day strength, right? Okay, so we know the difference that I told you, and because of boundary conditions and Platon restraint effect, cubes are actually going to give you, what will happen is when you put it in the compression testing machine and you test it, at the boundary of the platen and the cube, you're going to develop a lot of lateral friction. And the friction is going to put confinement in the cube. So the actual failure strength will be much higher than that of actual true material property, right? So that is why tubes are typically, will give you 25% higher strength than the actual material property. So, but that's why if you have to test a cylinder, which is 100 by 200 or 150 by 300, you get the true representation of the material property, right? So cube strength is about 1.25 times cylinder strength, UHPC. For UHPC, we have tested in the last 7-8 years. Interestingly, what we are finding is, because the size of the aggregate is very, very small, less than 2 millimeter, we are not really getting that beneficial effects of your friction. So what we are finding is the cube strength is sometimes slightly higher, sometimes lower, but they are nearly same. But typically in literature also we found that cube strength is only about 5% higher than that of your cylinder strength. So we take that nearly that of the same strength. Right, so this is the stress strain curve. Now, in a normal concrete, if you look at it, which is stiffer material. No, okay, let me quickly before, in a typical volume of concrete, which is going to occupy a larger volume? It is aggregate. What would be rough percentage of proportion? 60 to 70%, it will be actually the coarse aggregate is what it's going to be there. Then cement, in a typical mix, what is the maximum cement content we use per meter cube, let's say? 300, 350, 400, 450 is on the higher side actually. Precast maybe 400, right? It's only 400 kg per meter cube, right? So you see here. So the majority of the composition is actually from coarse aggregate. And even if you look at the hardened cement paste, that is going to have a lower strength and stiffness than that of your coarse aggregate, right? So, but concrete, now what will happen is the crack will start at the interface, which is called interfacial transit zone, and then it will grow into micro cracks and macro cracks and so on, and you will have non-linearity will come in, okay? So usually the stiffness of the concrete is going to be in between that of your coarse aggregate and hardened cement paste. Okay. Now again, why I am talking about this is the elastic modulus of the concrete is also a function of your compressive strength, right? So it is also going to vary depending upon at what time that I am doing the analysis, right? So that we have to keep it in mind, right? So if you look at it for normal cement paste, the elastic modulus varies from 15 to 25 gigapascal. For UHPC cement paste, now I put a lot of things together. That goes up to 30 to 45, and if I'm doing the same curing process under pressure and heat, then your modulus also is going to go up. So what I'm trying to say is your evolution of mechanical properties is also a function of how we are curing the concrete. If I'm doing steam curing, the mechanical properties are going to be better. If I'm going to do just moist curing, room temperature curing, then the mechanical properties may not be that high. Right? Similarly, if you look at the aggregate, depending upon what type of aggregate that I'm using, your elastic modulus will change, right? So that's why if you look at it for a elastic modulus of concrete per se, for conventional concrete, that typically what we use, it varies from 25 to 35 gigapascal. You know the formula 5000 square root of FCK, which is directly a function of your compressive strength. But UHPC, we are getting 45 to 55. So that's why for flexural members, actually it is the fractural rigidity, E into I, is what will govern the performance, the stiffness. But in a typical reinforced concrete, I will be I cracked. The cracked moment of inertia is roughly about 15 to 20% of your gross moment of inertia, roughly, right? When I use UHPC with pre-stress, now I get E is also going higher. Let's say if I take 25 and 50, E becomes twice. I also, because I put a lot of pre-stress, pretty much I can use the gross moment of inertia, not the cracked moment of inertia. So I get tremendous improvement in my flexural rigidity. So that's the reason precast, they can go and do a very optimized design if they combine UHPC and pre-stressing. So that's the idea now. People are actually want to go for UHPC. Okay. Right. So this is a quick summary. I mean, just I've taken typical representation. If you look at your 25 megapascal concrete, this blue color curve, this is the way it is going to be, stress strain curve. And for high strength concrete, if you look at it, the green colored curve, it is going to be like this, and it's going to fail in a brittle manner. Okay, so that means after the peak strength is achieved, the degradation in strength at higher strains is going to be much faster. So the post-peak behavior, it is going to exhibit a strain softening behavior. So strain softening behavior means at higher strains, the stress will keep coming down. Okay, but if you have low strength concrete, you see that the decline in strength is not very steep. So lower the strength of concrete is less brittle it is. Okay. So in UHPC we said, I told you, we put a lot of fibers, right? So a lot of fibers we add. So these fibers, what do? They help me in arresting that crack. Even if you look at in compression, actual failure mode is not by local crushing per se, but it is actually the tension is what actually inducing the failure even in compression. Because the lateral direction, because of the Poisson's effect, though I put it in compression, I am going to develop tension in the lateral direction. That is what it is going to create the failure, right? So if it is developing, if I have a lot of fibers, that fibers are going to actually arrest that lateral cracking that is good, lateral tension that is going to develop, then the material is not going to give up very quickly. So it is going to behave in a more ductile fashion like what you see here in tech. Though I gain high strength, but the material strength is not degrading quickly, it stretches up to a certain point. After that, you develop so much crack, and depending upon the characteristics of the fibers, now the fiber length itself, I told you, it is only 13 mm length, right? So it cannot keep on arresting that crack. So after a certain point of time, what will happen? It will give away completely, right? So that's what it happens here, right? Okay. Anyway, so normal concrete, high performance concrete, and UHPC that we talked about. Higher the grade of concrete, lower is the ductility and higher the stiffness. As you can see, the green color curve, elastic modulus is going to be much higher than that of your blue color curve. And this is the range of your elastic moduluses that what we talked about, right? Okay. Now, this is again, I am rephrasing whatever that we have discussed. This is based on the test that was done previously in the literature. You can see they have taken from 20 megapascal to as high as 90 megapascal. And if I put a cylinder and apply a load and measure the strain and then plot the stress strain curve, you can clearly see that as the strength is going up, my stiffness is going up. In addition to that, the strain corresponding to peak strength is also going to go up. However, ultimate strain is going to come down. What is the meaning of ultimate strain? Ultimate strain can be defined in multiple ways. Typically, we take 20-25% drop in your stress. That strain corresponding to the drop in stress, we call that as an ultimate strain. So you will find that higher the strength of the concrete, higher is the strain corresponding to the peak strength, but lower is the ultimate strain. So the difference between the ultimate strain and the peak strain is going to be much lesser. So the concrete is going to become more brittle. So right after gaining its peak strength, it is going to give away very quickly. So when I use high performance concrete or high strength concrete without any fibers, then this aspect I need to keep in mind. Because when concrete is failing in compression, is a very, very brittle mode of failure. We always want failure to happen in tension. So that's the reason we put a lot of higher factor of safety for systems that are subjected to heavy compression. For example, if you look at columns, that means I need to have higher factor of safety, because column is a compression member. Compression member will fail in compression mode only, right? Unless you have significant other bending. So we need to have higher factor of safety, right? Anyway, so this factor again, I need to keep that in mind, especially when you're designing a column with special concrete, high strength concrete. Then if I'm using 90 megapascal concrete and 30 megapascal concrete, which one should have a higher factor of safety? Which one will fail in a brittle mode? Is 90, right? So 90 megapascal should have a higher factor of safety, right? So that's what we tend to do. Okay, so this is from design aspects. So you know that IS 456 gives you, this is a characteristic curve and this is your design curve. Now how do we get this 0.67? I told you what is the actual strength, actual material strength. It is the cylinder strength. And I told you cube strength is going to be 25% higher than the cylinder strength, right? So actual strength will be cylinder strength. Actual strength is going to be I divide 1 by 1.25. So it is only 80% of the cube strength is the actual material strength, right? So we take 0.8 FCK is the actual strength. Then instead of 0.8, why do I have 0.67? Huh? What is that? So we also put, because see, what is that we are doing? We are making small cubes, right? The small cubes, when I'm making it, I'm going to have better quality control. But actually, if you look at the size of the member, they're so huge, right? So the larger the size of the member, more is the possibility of having more defects. Maybe you may not be able to compact it well and so on, right? So that's why there is one more 0.85 factor comes. 0.85 multiplied by 0.8 gives me this 0.67, right? So anyway, so that's the characteristic curve. Then what we do, again we knock it down by material safety factor, which is 1.5 for concrete to get 0.44. So if you see, even in the characteristic strength, I'm using only how much percentage? I'm using only 45% of the compressive strength in my calculations. So why do we have such a heavy margin of safety? So see, this is the characteristic curve itself. I'm doing only 5% in failure, right? In that also, what I'm doing, I'm knocking down, I'm using only 45%. So why is it so?
Long-term durability will reduce it. Long-term durability will reduce it.
Now this is durability comes from your how good is your microstructure and how your cover, all those things, right? But here I'm saying, why do we need to have such a low strength? I'm using, in the characteristic strength itself, I'm using only 45%. Why is it so? Right? Because concrete is a man-made material, and you don't, most of the time we don't make it in factory. A lot of variability is there, and when it is failing, it is going to fail in a brittle mode of failure. So we need to have a lot of factor of safety, right? Anyway, these are the design stress strain curves that we use, right? And typically for concrete strength less than 40 megapascal, we can use this, right? Which is a parabolic model, and the peak strain corresponding to the peak strength is taken as 0.002. Okay, so anything that is above this 0.002 strain, we keep it to be constant. Now again, if you go back, this is in strict sense, it is valid only for low strength concrete. But the code is saying that, okay, the purpose of the code is to keep things simple, so that the design engineers, they don't make mistakes, right? So code is saying, okay, now let me keep it same, even for concrete strength up to 60 megapascal.
So these factors are valid for high performance concrete and UHPC.
UHPC, no, we have to do a lot of work. I don't know. Material safety factors, I don't think so. I have to check the codes. I don't know. French codes, I don't know how much they take. Do they take 1.5? They also take 1.5. I think that's what he's saying. So, but because the variability in the strength is also going to be come down, probably my characteristic strength will be getting close to that of mean strength. So there I may gain. But this, from design philosophy point of view, I think partial safety factor will still remain the same, I think. That's what I'm saying. Okay? Anyway, so now this is for IS 1343. You know that the code allows up to M80 concrete, right? And it is clearly mentioning that, you see here, the design parameters that are given is not strictly valid for concrete grade more than M60. In fact, I told you more than M40 itself, it's strictly not valid. But again, because we have not really done a lot of validation of pre-stressed precast components which are made from high strength concrete and validated with the experimental results. So that's still a lot of work needs to be done. Okay, so that's why the code is saying that you can choose specialized literature and experimental results to calibrate your stress strain curve model. So this is, again I'm telling, because precast now there is a tendency to use more and more high strength concrete. If I'm using IS 1343, in strict sense, I cannot use the design properties that are given in code as it is for concrete grade more than M60. Okay, so that we need to do. So we need to develop our own models typically for concrete strength higher than 40 megapascal. Now IRC 112 also. So IRC classifies it in 3 ways. If you look at this is for bridge, Indian Road Congress bridge code, if you look at it, they also classify the same thing. Standard concrete up to M50 and high performance concrete, again I told you, same grade, I can have a standard concrete and high performance concrete. What could be the difference?
The addition of fibers and water addition.
Fibers are not there. In fact, addition of your supplementary cementitious materials to get more calcium silicate hydrate, so you'll get dense microstructure, so that will have better durability. So that's what it is, right? Okay, so they also have the same stress strain curve block. For example, if you look at it for concrete, they give, depending upon the load combinations, for basic and seismic combinations, still the partial safety factor is 1.5, just like we had for IS 1343, and it is 1.2 for accidental loading combinations. During construction stage, if you have some accidental loads, then for that you can take a lower material safety factor. So that's what it is. Okay. Now, this is the code, the stress strain curve property that are specified by IRC 112. And if you look at it here, we have multiple, this is the table that is reproduced from IRC 112. So if you see here, different properties that are directly given. What is FCK? FCM is the mean strength. I told you characteristic strength is going to be lesser than the mean strength. So obviously mean strength is going to be higher. And FCTM is the tensile strength, mean tensile strength, and this is a 5 percentile strength, this is a 95 percentile strength. Obviously 95 percentile strength is going to be higher than 5 percentile strength, right? So this is on the left side and right side of your normal distribution, right? Now, so one point to note down is the most important thing for compressive stress strain curve is this. This is what we are going to use. So just like your IS 1343, here also IRC 112, it says that up to M60, you take the peak strain as 0.002 only, and your ultimate strain is 0.035. But however, it is because bridges, we go for longer spans. So the moment you go for longer span, I need to go for pre-stress. If we go for pre-stress, invariably we need to go for high strength concrete. So that's the reason IRC code allows up to M90. But what they do is, they recognize the fact that there is a change in the stress strain curve response. Right? So this is actually 2 divided by 1000. So this symbol indicates that I need to divide by 1000. So 2 by 1000 is 0.002. Right? So what they recognize is the strain corresponding to peak strength increases with increase in grade of concrete. So for example, you see M90, the peak strain is 0.0024. But if you look at the failure strain, ultimate strain, it is only 0.0026. So if you see the difference, like what we talked about, the difference between the ultimate strain and peak strain is going to be lower when you go for high strength concrete. So that is what the code is also capturing it, right? And this is for again special concrete. Typically we use this parameters. These are some exponents that are given for different stress analysis, okay? So now let's, in the interest of time, let me just focus on the main important aspect. So this is what is important. So up to M60, though there is a change, if you see here, code wants to keep it simple, and that's the reason peak strain is taken as 0.002 and ultimate strain is taken as 0.035. Now important thing is the flexural strength, okay? When we do the design, I told you, for pre-stress precast systems, let's focus on the horizontal elements, which are beams and slabs, right? For me, the stress properties are governed by how much is your flexural strength, right? So flexural strength is the flexural tensile strength of the element, right? So typically for material property, we use this 4-point bending prism test and get at what stress it is going to crack. Because it's an unreinforced, the moment it cracks, there is nothing to prevent that crack, so it is going to be a failure, right? So we calculate it. And this is the way, typically we do this 500 mm, 150 by 150 prism, and we do. So this is a stress strain curve for flexure for UHPC, and this is for a conventional concrete. For a conventional concrete, you don't have any fibers. So the moment, typically flexural strength is about 10% of your compressive strength. So if I am taking 40 megapascal, my flexural tensile strength is roughly about 4 megapascal. So that's what we have modulus of rupture in your IS code. What is the expression for modulus of rupture? 0.7 square root of F6. So if you put it, the number will work out to be roughly 10% of your compressive strength. But the direct tension strength will be 5 to 6%. But flexural tensile strength will be about 10%. So because you don't have any reinforcement, right after cracking, it will fail. But UHPC, you see, though the same UHPC, if I am testing it in bending, Now I put 2%, 2.5%, 3% of the steel fibers. Even after cracking, what happens? A lot of multiple cracking will happen, and you're going to gain in strength, and then it is going to come down. So what does this blue color actually represents? It represents like when you test a steel rebar, what do you get? You have elastic behavior, then you have a yielding, then you have a plastic portion, then you have a hardening portion, and then it comes down, right? In the same way, in UHPC, depending upon how I tailor the mix, I can get this multiple cracking, I can get my hardening response, and then a strain softening response. So if you look at the energy within this curve, the energy within the curve is calculated from the area under this curve. So he is going to go for your UHPC, you are going to have like an order of magnitude higher than that of your cementitious, normal conventional concrete, right? So in nutshell, when we are doing the flexural design, particularly from ultimate strength point of view, right? Typically what do we do in flexural design? We ignore the area which is below the neutral axis. Now, even after cracking, because the system is giving me so much strength in tension, I don't need to ignore the area of concrete below the neutral axis. I take effectively the stress contribution that is coming from UHPC in my calculation. So that's how you end up with a more economical design, more optimal designs with UHPC, right? Okay, so now let's just quickly look at some of the work that we've done. This is for a typical 140 megapascal concrete, what we have developed in our lab. And you see here, we looked at what are the effect of different types of fibers. Okay, this is actually work of a couple of master students. I think Pawan is also here. He's already now working on characterizing these things. This is for the same UHPC. I put this brass coated this fiber, the small fiber that I circulated. No, these are 0.12 millimeter and 13 mm in length. But these are the costly element in the UHPC. So now, can we replace this costly brass coated small steel fibers with normal steel fibers? Because again, from Indian point of view, ours is a very, very cost sensitive market. If I want to promote this material, then I need to somehow optimize the cost of UHPC. Now, what are the ways and means with which we can actually reduce the cost? Is one way, because the 30% of the material cost actually comes from the fiber, which are basically imported right now. Now, slowly, I think some manufacturers have started producing these products. Anyway, so for 2% you see here, flexural strength I get as high as 14, 15 megapascal. For a 140 megapascal concrete, that's what I told you. Flexural strength is going to be 10% of my compressors. That's valid for even normal concrete also. That's the same 10% we are getting here. These are 3 specimens, some variations are there. So I'm taking an average response. Okay, and we also looked at all the crack patterns and other things. Okay, now this is the crux of the issue. These straight fibers are costly fibers. These hooked end fibers are the normal, the bigger, longer fibers, right? If you see in flexure, what we are finding is these are about let's say some 80-85 rupees per kg. These straight fibers are roughly about 140 rupees, maybe, Muthurajan? 150 rupees. So roughly double the cost. Now, if I can replace the straight fibers with the normal hooked end fibers, also, if you see here, I'm getting nearly the same performance as that of this. If you look at the energy absorption, the area under the curve, 64, 58, 60, they are all nearly the same. So, in flexure, I don't really need to use this costly brass coated fibers. I can still optimize the performance with. And this hybrid is basically combinations of straight and hooked end fiber. So here, in fact, in flexure, in fact, hybrid was showing higher performance even than that of your hooked end or straight fibers. And this is again some ways and means of how do we evaluate the performance of the fiber. When you do the flexure test, you get your load displacement curve, and then you have different parameters. Okay, at a displacement corresponding to first crack, you keep that as D. Then you take 5.5D, 10.5D, and you calculate all the area under these curves. Then when you measure it, you find that the hybrid ones, okay, are actually giving nearly same performance or maybe somewhat better than that of your straight fibers. So that gives us a lot of confidence that hybridization of the fibers can actually pave the way for reducing the cost of UHPC and for more broader applications in precast industry. Okay, and we also did direct tension because I cannot directly use the flexural strength. Flexural properties are important when I do the calculations at the transfer stage. When I am doing the strength calculations at ultimate, I cannot do the flexural properties. What I have to do is use the direct tension properties. Now, then we need to characterize this material under direct tension also. Okay, typically why we don't do all these things for normal concrete? Because we don't consider the tensile strength of concrete in any of our ultimate strength calculations. I don't need to worry about it, right? And already it's very well established what is the tensile strength also. For UHPC, depending upon if you do it, you have a lot of variations are there, right? So again, this is what we have talked about. And this is again in pure tension. So if you see here in pure tension, you get about 6 to 7 megapascal. Again, this curve is only a typical curve. If you're talking about 200 megapascal concrete, this value is going to be high or different. Because UHPC definition is anything that is more than 120 with satisfying some durability requirements and flow requirements is called as ultra high performance concrete, right? So anyway, so you get 6 and then go on. So I have to characterize this, how this behavior is. What is the first cracking strength, how much hardening that I'm getting, and how much softening I'm getting. So depending upon that, only I can derive my constitutive relationship for tension so that I can use it in my calculations for designing the element. Okay, so that's the whole idea. Okay, so this is for direct tension test. Maybe I think I'll just quickly show. So again, in direct tension test, surprisingly what we found was, in fact, the straight fibers were actually performing better than your hooked end or hybrid fibers. Because the straight fibers are smaller fibers, they are distributed very well. For the same volume in a particular cross section, when you look at it, now more number of straight fibers are actually going to cut the crack plane. So that is why straight fibers were performing very well in direct tension. But if you look at in flexure, in bending, the difference between the type of fibers were not significant. But in pure tension, actually the straight fibers, the smaller fibers, are actually performing better than the hooked end or your hybrid fibers, right? Because you have more smaller fibers, now more fibers are bridging the crack. The space between the fibers is less, so they are more effective in transferring when you have a direct tension where the entire cross section is subjected to the same strain or stress. So whenever you have a strain gradient in flexure, the fiber type doesn't play much role, but whenever you have a constant strain in pure tension, then the straight fibers, more number of fibers actually plays a better performance. So these are all the things that we need to know. But because now you see from ultimate strength point of view, I need to use only this direct tension test. I cannot use other things, right? So we have to be careful. Okay, so this is some again straight performance. The same thing, you can see that first cracking was about 6.72 and it went up to 8 megapascal. And then at about 30% drop, I get about 5.63. Of course, if all these values A, B, C are higher, it's better for me. Then the fibers are actually performing well. And also, the strain corresponding to this F30, epsilon 30 is also a very important parameter, which should also be as high as possible, right? So now, I need to develop the mix that is going to give me better performance in terms of this variable. So here also you can see that performance was good, but hooked end was not performing that well. For some reasons, again, we are doing more tests on this to really find out why the hooked end fibers. So hooked end fibers, the small fibers with hooks. We were thinking that should actually perform better. At least I was expecting that this C, the residual strength and the strain at which it's going to fail is going to be much higher. But surprisingly, we are not getting it. So that again, we are looking at it, what could be the reasons why.
I have one question.
Please.
Earlier, for the direct compression, you said for UHPC, there is a sudden drop. In one graph, you had shown that parabolic, plastic, there is a sudden drop.
Yeah.
But in direct tension, they are having a much gradual drop.
Correct, yeah.
Why
So that's,
that
yeah.
sharp drop in direct compression?
Okay. That in our data,
Like I would wish that UHPC should also have a gradual drop in direct compression.
Ideally, yes.
ideally that's what I think, yeah, that's an idealization, Professor Ramlan. Actually, it's an idealization that I gave. From whatever testing that we have done, we are also getting a
Gradual drop.
gradual drop only, right? I think Uttaraja, can you clarify?
Yes, sir. We are getting post-peak response.
Now the question is flat and then sudden drop. We don't get that sudden drop. It's an idealization. It's an idealization. Yeah.
Sometimes if you have higher energy, your machine also not able to control that. It is fading suddenly. So the energy dissipation is also very high. So
Hey, that point is well taken. But what is it? It was remaining flat and then falling sudden. It doesn't happen. It reduces and then it gives away after there's something called strain localization. After so much crack, it will become unstable and then it will give away. But that flat portion was idealization. Yeah. Okay. Anyway, so let me keep going. So this is for the hybrid fibers. So again, here also we are getting nearly the same performance as that of your straight fibers. Anyway, so with that, now let me get into the long-term properties. How much time? I'm going a little slow. Another half an hour I can take? Okay, hopefully. Hope I'm not boring you.
No, definitely not.
Okay, fine. So let's talk about long-term properties. Okay, we talked about short-term properties in compression and tension in flexure also to an extent. Now for fiber reinforced concrete also same. But in a normal fiber reinforced concrete, we typically don't go more than 1% of fiber dosage. If I want to get this kind of strain hardening type of response, then I need to put heavy volume of fibers in the dosage. Then the cost goes up. So that's the reason normally in fiber reinforced concrete, your volumetric dosage of fibers is typically 0.5%, 0.75%, or maximum 1%. But UHPC, I cannot afford to have a brittle failure, because again we deal with high strength. Already we are dealing with a high costly material. So adding little extra cost for fibers is not going to hamper the performance, right? It's going to only help me. So that is the reason it becomes practically possible to put such high dosages in UHPC, but in a normal concrete if I do, the cost. And also because the tensile strength is also not very high, right? So that's the reason FRC. But in FRC also, if you put a lot of fibers, you will get very good performance improvement. But it is more advantageous when I do it in a high strength concrete, because now I'm using the tensile stress strain response also in my design applications. Now,
More than 0.5% of fibers would reduce the strength of the concrete.
steel, actually steel fibers, when you mix it properly, when you don't have walling effect, right, then the strength should not come down. Okay, and we have tested several of them. Strength goes up by 5-10% depending upon how your mix is, but strength doesn't come down. But when you are using polypropylene or synthetic fibers, then you have a weaker interface. Okay, then the strength reduces slightly. But when I'm using steel fiber, strength typically doesn't come down. It can go up depending upon your mix.
Okay, sir. But addition of such a high percentage of fibers will plan for very low workability.
Correct.
Very high dosage of admixtures will also reduce the strength of the concrete, right?
Correct. So you have to tweak it. Yeah, that's a very good question. Yeah. Higher the fiber dosage, then workability goes down. Then I need to put more super plasticizer. The more super plasticizer, the mix will not set. So you have to tweak your mix design. So that's why mix design is very important. Right? Yeah. So it depends upon your application. So let me put it there. Okay. Now, creep, long-term effects. So long-term effects, typically, we have creep, shrinkage, and relaxation. Concrete, we are worried about what is happening in creep and shrinkage. Okay. Now you can see. Yeah.
Creep, shrinkage, and
Relaxation. Relaxation is a property of a steel. Typically steel we are worried about. Briefly I'll talk about it. Okay. Now why are we should be concerned about creep strength? From again precast point of view, I told you, when Professor Amlan was discussing, it's very important. We go for longer span, right? So right after the application of the load, what you have is an immediate or short-term deflection. But if you're not careful about creep, if your material has a lot of cementitious system, they undergo creep more. And if you have a lot of unutilized water, then they creep more. In fact, by putting more coarse aggregate, you can reduce the creep significantly. But in UHPC, we go the other way around. But still the creep deformations in UHPC will be less. Okay? So anyway, so what you see here is, under sustained load, say apply some load, if the system is elastic, depending upon the support conditions, you can derive what the elastic deflections are going to be. If the loads are kept same, over a period of time, you will find that the deflection will keep increasing. So why does it happen? Right? Why does it happen? Load remains same. So you must have done some strength of material slab testing and all, right? Higher the load, higher the deflection. I'm saying I'm stopping the load and I keep observing the deflection keeps increasing. Why does it happen? Strain will keep increasing. Why should the strain increase?
Because of adjustment of
Calcium hydroxide? No, calcium hydroxide converts itself to additional CSH, it's better, no?
calcium silicate ideas into their adjustment will take for sustained load.
Why does that adjustment happen? So what we are saying is that there is some softness happen to the material, or in other words, the elastic modulus of the material reduces. So if you go back, this is one thing that, so we said definition of creep itself is under constant stress, your strain keeps increasing, right? So if I look at this stress strain curve for concrete, so let's say you have this. Now I apply certain load, okay, and I keep it here. So let's say that I apply FCI, the stress, and my initial strain is epsilon Ci. Now what I'm saying is, under this constant stress, the definition of creep is, my strain doesn't remain at epsilon Ci, the strain is going to keep increasing, right? So it's going to go like this, right? Let's say epsilon C2, okay? Now what is the definition of your elastic modulus? Right? It is the slope of the stress versus strain, right? So the stress remains constant. Now the strain, initial strain was this, epsilon C1. Now what has become? Epsilon C2. So what is the elastic modulus now? FCI divided by epsilon C2, which is much larger than that of your epsilon C. So what happens to your elastic modulus? It actually reduces. So when the elastic modulus is reducing, means what does it imply? The material is actually softening. When the material is softening, means what will happen to what will happen? You're going to have more strain for a particular stress, that's what we are saying indirectly. And you're going to have more curvatures in the beam, that will lead to more deflection. So curvature and strain is function of your curvature, curvature is function of your strain, and deflection is double derivative of your curvature along the length of the span. So you get more deflection. So that's what happens, right? Anyway, so long-term property, again, this is what happens, this is what we told, elastic deformation is this. Right after the time, if I start plotting the strain, this epsilon C2 as a function of your time, this is right at the time of your load application. So immediately at Ti, when I start applying the load, depending upon how much I apply, the epsilon I will be there. Though I am keeping the load constant, what will happen is the strain is going to keep increasing. Now that increase will be faster initially, then it will gradually reduce, right? Then after a certain point of time, if I remove the load, I can recover all the epsilon instantaneous, which is called elastic recovery. And then some strain I will recover, which is called creep recovery, but still I will be left with a lot of permanent strain in the system. That is what will create deflection, okay? So this is your creep versus strain. Now, depending upon, I told you, we design the structures for, let's say, 50 years. I want to do the calculations at, let's say, 3 years from the day of construction. Right? Now, how do I calculate? So, let's say you have a bridge that is an existing bridge that was open to traffic 3 years ago. Now, an engineer, the state department is calling you and saying that there are some deflections. And you want to understand what are the effects that are going on. So at the 3 years, you need to understand what are the level of creep deformations would have happened. So how do we do that? So somehow I need to have a mechanisms to see how the creep is evolving over a period of time, right? So that's what people said. So okay, I need to do. Okay, so that's why the total deformation, typically we divide it into two parts, as I've told you, elastic deformation due to load, and then the another one is because of the creep. Okay, now what are the factors that affect the creep? I think this is, the major factor I told you is, if I want to have a less creep, I need to have more coarse aggregate in the system, and another thing is less water to binder ratio, or I cannot have unutilized water more in the system, right? So that's what it is. So longer the curing time, lesser will be the creep. Somehow if I cure it well, then allowing the water to be utilized better, then also we said steam curing is going to reduce the creep, okay? So this is what in UHPC, when I am doing steam curing, my creep deformations are going to be very, very less, because the creep strains are going to be less, okay? Now typically for high strength concrete, we are going to use low water to binder ratio. They tend to have smaller creep than the normal strength concrete. And again, creep also will increase with temperature, because the temperature, that it is going to increase the rate of creep. So that is there. And higher the humidity, lesser will be the pore water which can escape from the concrete, and less creep. So why the humidity has to play a role? Okay, what is humidity? The definition of humidity is the amount of water vapor in the air, right? So if air has a capacity to absorb some moisture, right? If it is already fully saturated, then it cannot absorb any moisture, right? So that's the reason for a place like Hyderabad, which is a very dry weather. Typically in Hyderabad, the relative humidity is 40-45%. If you go to Chennai, it will be about 80%. So where will you have less creep? In Hyderabad or in Chennai? In Chennai, because your relative humidity is already high and air is already saturated with moisture, it cannot absorb any more moisture. So the creep deformations are going to be lesser, but in Hyderabad we'll have more shrinkage and more creep. That is one disadvantage, you can see. Okay. So concrete with high content of cement paste will have creep, that I told you. If I want to have less creep, you need to put more coarse aggregate, which are inert particles, which are not going to creep. But again, then I may not get the flow and other properties, right? Addition of reinforcing bars in compression area will reduce the creep. This is a very interesting thing. I told you creep is going to create additional compressive strains, right? Now if I have reinforcement that is there, that will relieve that strain that is happening on the concrete on the compression side. So it will take some load. So in that way, it will reduce the softening of the concrete due to creep. So you will creep. That's one way. In fact, our IS 456 or IS 1343 also, it actually rewards people if you put more compression reinforcement in your beam. Your deflection equations, when you look at it, there are L by D factor that we have to use. The modification factors are higher. So the code actually helps you to come up with less thickness if you put more compression steel. Only the factor is it is going to help you in reducing the long-term deflections. Okay, right. Okay, this is the thing. This is another important thing. If I have a member for a constant volume, more surface area, more the surface area, more is a passage for the water to escape the system, right? So for a particular volume of a concrete, I take two cases, same volume, 1 meter cube, 1 meter cube. This one is having lower surface area, another one is having higher surface area. The one that is having higher surface area will have more creep, because it is having more passages for the water to escape from the system, right? So that is also this. How does the code takes into account? That's where there is a factor called notional size coefficient. So that H naught is a factor that typically we use that accounts for this effect. Okay. larger the surface area, then you'll have more creep. Okay, so this is a creep coefficient. So somehow, how do I account for that in design? This phi captures how the strain is evolving over a period of time. Higher the strain, then I told you the elastic modulus will reduce by a factor. Typically, we take 2.5 like that. So you can see simplified expressions given in the code are this. And there is also one more factor. It is also function of your age of loading. Why does the age of loading has to come into picture? How much time it takes for concrete to cure for a normal concrete? For normal concrete, why do we use 28 day strength? Is there any reason why we use 28 day strength? In 28 days, we will almost 99% of the hydration is expected to be over, right? So that's the reason we take. In addition to that, there are other reasons also. Anyway, so if I start loading at young age, my creep is going to be more. Why? But at the young age, my hydration is not complete. More water is there. If I start loading, already you have created a disturbance in the system and you're creating more passages for the water to escape out of the system, right? So that is what you're going to have, 7. So that's the reason at low age, if I start loading, my creep coefficient is going to be high. So if you want to reduce the long-term deflection, then what should we do? You should delay the loading, right? So you should not remove the scaffolding. You should not remove your formwork quickly. So in this day and age, everybody wants, even for cast in place concern, they're looking at 3-day, 4-day cycle, which is not correct. They want, exactly, but this is not good from creep point of view. If you start talking about creep and all, they'll say, you don't know the. But this is, in fact, we were involved in a couple of projects in Dubai. The major problem happened because they started removing the formwork early. At 14 days, they started removing formwork and the slab started caving in. See, if I strength, I can put by multiple ways. Deflection, how do you recover? It's a major problem. So people think that removing the shoring is a very, very important thing. Not many people understand that. So always you have to test cubes before you remove the shoring, formwork shoring. Right, anyway, so basically, in addition to that, creep depends upon stress in concrete. I mean, higher the stress, again, when do you have micro cracks in the system? Let's say I load it in concrete in compression. When do you develop micro cracks or interfacial cracks? Typically, when the stresses are more than 40% of your compressive strength, you develop all these cracks. So higher the stress, higher will be the micro cracks in the system, then more is a passage for the water to escape out of the system. Then age at loading, I told you, and duration of loading, depending upon whether you are calculating at the end of 1 year or 2 year or 3 year, longer the duration, longer it will be the creep deformations as well. Right? And typically, that's why he said, when the applied compressive stress is less than 1/3 of the compressive strength, then creep can be assumed to be proportional to the applied stress. So we measure in terms of this creep coefficient, how the concrete strain is evolving as a function of time with respect to what is the initial strain. Epsilon Ca is the strain at the time of initial loading. Right? Okay, so let's say this, let me not get into it. So in simple words, how does the code takes is, what we take here is phi naught is a maximum creep coefficient that can happen at the end of 5 years. Okay, so this is a maximum value. And beta is nothing but some kind of a reduction factor. So depending upon whether I am doing it at a 1 year or 2 year, I need to put this reduction factor. That's as simple as that. So this is a maximum value and I reduce it by some factor. So for example, if you see here, at about 40 years or so, it reaches a maximum value of 3.12. If I am doing calculation, let's say 1 year or 2 year, it may be 2.6, 2.7, I don't know. So that reduction, so the 3.1 has to be reduced to the actual value. This is the actual variation of your creep coefficient. And phi naught is the notional creep coefficient that happens at 70 years. Okay. So depending upon when you do the calculation, you apply some reduction factor. So that's it. Now this reduction factor, again depends upon multiple factors. One is the relative humidity that we talked about, and the compressive strength that we talked about, and the T naught is the time of your loading. So these are the three important factors. So the code gives you some expressions for your phi naught, and then you apply your reduction factor. So the reduction factor, again, some lot of empirical equations are there. In nutshell, it's very simple. Higher the relative humidity, less will be the creep, right? More dry the air is, higher will be your creep. Okay, so that's how it's being incorporated. In addition to that, there is a H0 factor. What is that H0 factor? That's what I told you. What is another factor that affects the creep? It is the volume to surface area. The H0 is nothing but your volume to surface area, right? So now if H0, if I defining that as a volume to surface area, if H0 is higher, what is that implication? Surface area is smaller or higher? Volume, H0, I defining that's volume to surface area, right? So if denominator is small, what will happen to H0? Will go up, right? So if H0 value is higher, what will happen? Which will have higher surface, right? Volume to surface area, right? So you have to look at it. Sorry, surface area if it is lesser, H0 will be higher, right? So that's what we did. So basically this is what you see. U is the perimeter of a cross section of a member. Perimeter, if I take a unit length, then perimeter becomes your surface area. A0 is your cross section area. So that's a volume. This is a volume to surface area. So nothing but a measure of volume to surface area. So if surface area is less, H0 will be higher. So then your surface area is less will be the creep, right? So that's what you have here. So other factors are also there. So let me not. So this is a figure that represents. For the same volume, if you look at it, if your H0 is higher, your creep is going to be lower. If H0 is lower, your creep is going to be higher. That's what it is. It's purely a function of your surface area, volume to surface area, right? Okay. So anyway, these are the again some more points. If the table, whatever the table that we talked about, these values can be used provided you satisfy these conditions. What are those conditions? The temperature has to be between 10 and 20, right? And your compressive stress cannot be more than 36% of your characteristic strength at the age of loading. And for temperature higher than 40 degree, these coefficients can be multiplied by 10%. These are all some simple guidelines. For normal concrete, the code is actually giving. I told you higher the temperature, higher will be the creep. So code is saying that okay, increase it by about 10%. In India anyway, temperature don't go more than 50 degrees. So that is the reason, you have the simplified factors, right? So anyway, so this is for UHPC. So you can see here, again UHPC, if you see the creep coefficient, this is very interesting. Typically for normal concrete, if you don't have any data, typically what we do is we take 2.5 and we do the calculations. As a design engineer, if you go and ask him for simple calculations, he'll start with 2.5 and then he'll do the calculations, right? But for UHPC, you see here, though we are putting lot of cementitious system, but my creep coefficient is very low. Why? And that also is function of the curing. If I'm doing steam curing, it's even less. Why? So you understand the question. For a normal concrete, creep coefficient 2 or 3 we take. For UHPC, though I am putting more cementitious content, which I said is going to create more creep, but still my creep coefficient is less. Why? Because your water cement ratio is first of all very low, and we put lot of supplementary cementitious material, that additional hydration happens for over a long period of time, and you form more products in the system, and you get more denser network, then the water, even if it is there, it cannot go out of the system, right? So that's the thing. Then steam curing is even better. So you form more better, denser microstructure. So your creep, that's the reason UHPC helps. I told you the elastic modulus is high. Because I do pre-stress I am going to use I gross. So EI, the flexural rigidity is going to be very high. In addition to that, my long-term deflections are very less. So it makes a lot of sense for using UHPC for long span application. That's the reason. But only thing is the fire resistance is still an issue. So we need to find ways of tackling fire resistance. Okay, anyway, how much time that you can? We can break. Satishilan, is he there? He's on the way. Maybe after tea, then I'll take 15 minutes, then he can take over. Yeah, all right. So we'll take a break, Professor Ahmed. Okay. All right, so yeah. Thank you.